Okay, hello everyone and welcome to this very exciting video of today. And it's my pleasure today talking about introduction to smart grids, architecture and features. And this video is specifically recorded and dedicated to everyone attending to this one-week international faculty development program on recent advances in smart grid and renewable energy integration. And this very exciting opportunity has been organized by the Department of Electrical and Electronic Engineering at Jakarta Institute of Technology in Bangalore. And my topic today, as I said before, it will be an introduction to smart grids, architectures, and features. I would like to say thank you to all of you for being here and also for sharing time in this amazing opportunity. Also, I would like to recognize and say thank you to the IEEE Power and Energy Society, also to the student branch of the IEEE and the IEEE System Council. So I am really excited today to talk about this smart grid, and also it's a very exciting opportunity because I will be presenting on this day first, on 2nd of August, I will be presenting this very simple but extremely exciting introduction to smart grids. And something that is quite relevant and interesting is I can see the total schedule, the program schedule for this exciting opportunity. And I can see that the day 5, there is an opportunity for hand-ons using real-time simulation. And I am really excited because I can see that the colleague from Quartz Systems, that they are representing Typhoon Hill, my dear friends of Typhoon Hill in Asia, in India specifically, they will be talking about advanced microgrid technologies. And also, I am extremely pleased to see that also Dr. Manish, application engineer from our friends of OpenRT, they will be presenting some information about real-time coordinated control of integrated renewable energy resources. So as you can see, my talk today is an introduction, but I can see a very strong connection with all the topics that you will be dealing later in this very exciting opportunity. So before I start, I would like to make a disclaimer over here, and I would like to tell you that all the opinions, all the ideas presented over here, they are coming from Francisco Gonzalez, from myself. So no institution is related to these concepts and ideas that I will be presenting over here. Something that is very important is that the slides of this presentation will be released later into my ResearchGate repository. Over here, you can see the address over there, the website. So I suggest that if you're interested on the slides, you can go over there. Also, if you're interested in some practical stuff that we are doing in the lab and also in the company, so I highly suggest that you go to the GitHub repository. Some of the things that I will be talking here related to digital real-time simulation, they will be located over there at the GitHub repository. Also, this is a pre-recorded video, and you will see this video also later in the YouTube channel, your YouTube channel. Over here, you can see the link. I highly suggest that you go over there. There are plenty technical material, starting from protections, going into many other topics. Then, if you are interested on what we are doing in research, development, and also innovation, please go to Twitter and follow us in the new name X, and also in LinkedIn. And finally, if you have a very interesting question or any comment that will allow us to improve, please feel free to drop an email. The email is located here at the very bottom, the last line of this slide. So, well, let's say a few words, because probably you are wondering why I am here, what is my job over here. And before I start, I would like to say a few words related to us, and also a few words about our research and also the enterprise. So many years ago, I used to tell to my students, if you want to know something about a very specific person, you can go to Google, because Google used to have the answer for everything. However, we need to be honest, technology change, and also today we are talking about smart grid. That is a natural evolution of the technology. We will talk that later. What I want to tell you is that right now is quite popular the use of something that is called ChatGPT. There are different versions. There are ChatGPT, there are DeepSeek, there are Copilot. There are many artificial intelligence-based website that they can bring to you a lot of information. And as you can see over here, my name is Francisco Gonzalez-Longatt. I have been working for many years in the field of electrical power systems. I have several publications and some awards, like the IEEE Peace Outstanding Engineer Award, but also I have been doing a lot of research in the use of technologies in order to improve the efficiency and the security of the electrical power systems. So I am Francisco Gonzalez, and I will be giving this lecture today. And here you can see some of my timeline. I started in 1994 in a very small country in South America, and I started my research, my teaching experience over there. My research team over there was basically related with software development, prototype development, and pure power system analysis. 2009, I was in the University of Manchester until 2011. Then Coventry University in 2013, I moved to Loughborough University in the United Kingdom. And during those stages, of course, the research was changing. I started to do more things about frequency control, HVDC, multi-terminal system, but also all the low carbon technologies that, like electric vehicle, battery energy storage, and so on. Of course, I developed my research team over there at Coventry University, Loughborough University. 2019 was a very interesting change, because in 2019, I moved to Norway. 100% of my time was at the University of Southeastern Norway. And over there, I have the breakthrough in 2021 to create and develop the DIgEnSys-Lab, Digital Energy System Laboratory, where I start to be more and more involved in digital technologies. 2022 is when I decide to go back to the UK at the University of Exeter at the south of England. And also I established in March of 2022 my company that is called fglongatt Ltd. 2023 is the change. I came back to Loughborough University, and again, etc. And all the universities I always create, my research team has several postdoc and also PhD students. Well, it's my pleasure to introduce the DIgEnSys-Lab. DIgEnSys-Lab is the short for Digital Energy System Laboratory. At the moment that we are talking today, 2025, we have a small place in the University of Southeastern Norway, but also one here, very small, at Loughborough University. But as I said before, also we are doing consultancy and also training. So here there is a small photo with some of the trainings that I have the immense pleasure to deliver last year, 2024. You can see here that I have been delivering training for the power utilities in Mongolia, Saudi Arabia, Thailand, and so on. So, but the topic today is related to smart grid. And a very interesting thing is that I have been involved with the history of the smart grid for many, many years. And to be honest, it's a very good question where to start and when to start. Because my first research project in the UK between 2012 and 2013, it was called Exploring Beyond the Frontiers of Building a Smarter Grid. And over here, you can see that I highlighted this ER at the very end of the word smart, because it was my strong belief, and it's still my strong belief, that a smart grid is not a proper term for the classical electrical power systems. The proper phrase should be smarter grid. But we will discuss that in a very few minutes. 2012 and 2013, the final outcome of that project was that we realized that creating the smart grid, we identified several issues. One of them was the uncertainty, the increased level of uncertainty created by the integration of renewable energies. Also, we realized that the massive deployment of sensors in the electrical system was creating a volume of so much data that create the issue of big data. And also, we identified that communication was a clear element in order to move forward and deploy and make up a successful smart grid. So in 2018, I wrote this very exciting book that is called Advanced Smart Grid Functionalities, based on Power Factory. And to be honest, we start to think about the concept of a smart grid. And basically, you can think about the smarter grid like when the energy finally meets the information. If you go to the book, the chapter number 1, Introduction to Smart Grid Functionalities, something that you can read over there is that it's very unfair to call the electrical power system a smart grid. And the reason is because the electrical power system has been for many decades, or probably more than a century, smart. Nothing is smarter than use the basic physics principles in order to make the electrical system works. If you go to protections, nothing is smarter to use the electromechanical protections. Electromechanical protections, they use the basic physics principles in order to identify detect electric faults. So to be honest, the proper concept must be a smarter grid. And if you remember some lessons of grammar in English, the suffix over there, this termination ER, smarter, what is meaning is that we are adding more intelligence to the electrical power system. And that is the reality. The reality is that the proper phrase should be smarter grid, because what we are doing is using some technologies in order to enhance the performance, the operation, the security, the reliability, the resilience of the electrical system by adding more intelligence. So let's start here. Our presentation today is called Introduction to Smart Grids, Architecture and Features. So let me see over here. If you look over here, let me show you the agenda.
So this agenda is quite ambitious. We have around 90 minutes today in order to talk about smart grids. And we will start with the conceptualization, the concept of a smart grid, considering basically two approaches, the one coming from the United States of America and the other one coming from the European Union. Then I will explain where the energy meets the information in order to create this concept of smarter grids. Then we will talk about the natural evolution of the technology related to electricity grids. We will talk about some applications, the traditional applications that you can find in the utilities, in order to show you the smart grid architecture, considering the American approach that is coming from the National Institute of Standards and Technology, but also the European framework that is coming from the standardizing groups in the European Union. Something that I will add is something related to cyber physical systems, because the reality is that the smart grid is a cyber physical system. Then I will tell you about something related to smart grid applications. I will show you something related to distribution systems and transmission systems. And then I will show you something related to digital twins. And finally, the closure. Okay? So without further delay, let's start our discussion about the conceptualization of a smart grid. Well, probably you are too young, but at the very beginning of the history of smart grids, to be honest, it was very confusing at that moment. I mean, 2004, 2005, that is probably the beginning, the born of this concept of smart grid. Everyone was confused, because if you look this image over there, you can see several people blindfolded, and they are touching the same animal, and in this case is an elephant, a beautiful elephant, but you can see that different people has different perception about the concept. And this is similar to what's happened to the smart grids, because if you are in the telecommunication, or you are in operation, or you are in informatics, you will have a different vision about the concept of a smart grid. So what I am telling you is at the very beginning, it was a bit confusing, and several visions about the concept and description of a smart grid start to appear coming from different companies and organizations. We can say that probably the first official reference about the concept of a smart grid was in 2005, and you can see that this very amazing paper published by Amin and the famous Professor Bruce Wallenberg, that is called Toward a Smart Grid. And in this very specific paper, the idea of a smarter grid was introduced, and the original idea was to add intelligence to the electrical power system. 2007, 2 years later, United States of America, they launched what is called the Energy Independence and Security Act in 2007. And in that document is the foundation and the vision for the smart grid from the United States of America. So what you can see is that is a modernized version of the electrical system, and the idea is to improve the reliability, the security, using communication as a key element between the different actors of the electric grid, supporting real-time monitoring, automation, and control to increase the integration of renewable resources. But we need to be extremely careful because we need to care about the cybersecurity and the resilience against threat. So that was the concept that you can see over here, the features coming over here from the Energy Independence and Security Act. The Department of Energy in the United States also, they establish a definition. So here you have side by side the definition coming from the National Institute of Standard and Technology, and you can say that the concept of a smart grid include the modernization, bidirectional flow of energy, use of two-way communication, control capability in order to create new functionalities and applications inside the grid. And that is the vision coming from the National Institute of Technology in the United States of America. The US Department of Energy, they define the smart grid basically as a class of technology. As you can see over here, we can see that this is an evolution. The concept of a smart grid is an evolution from technology. And in this case, what we want to do is to move the electrical system into the 21st century using computer-based remote control and automation. Well, 2006 in Europe, well, the European Union also defined the smart grid. And the smart grid by the European Commission in this amazing European technology platform for smart grid, they defined the smart grid as an energy network. The European vision is also integrating not only electricity but also heat, transportation, and the other energy vectors, because here in Europe the idea of integrating a different energy system and improve the performance was a key element for the policies of the European Commission. Automatically monitor the energy flows and adjust the changes in the energy supply and demand accordingly. So you can see that this definition is making the system more flexible in order to cope with variability and intermittency coming from the wind power and the solar power. And you can see this is 2006. So if you look the basic features defined by the European Union smart grid, it must be digital, interoperable, integration of renewable. We want to empower the customer because we need the customer to be more involved and in the power system operation. So we want to use those smart meters and the dynamic pricing in order to empower the customer and be part of the decisions. But also integrating many customers and also the possibility of the prosumer, I mean that the customer produce electricity and deliver to the grid, and that was an amazing step forward by the European Commission. And finally, very important is that having digitalized the network, having a lot of measurement and data, that will allow the use of data-driven methods for planning. So this was the Vision 2006, created by the European Union. So as I said before, we can think about the smarter grid as the moment when the energy meets information. And if you look over here, let me show you this slide. This slide is dedicated to the old paradigm. In the very old paradigm of the power utilities, well, you have here the electric generators producing electricity. The electricity moved to the transmission system. We have the distribution system coming from those substations, and we are going into the customers. In other words, the energy flow was very centralized, very one-directional, and also it was the same related to the information. Because we have those meters here downstairs located at the customer facilities, and from there what we are doing is moving the information upstairs. But the customer was just producing data that the information was used by the utilities. So the reality is that they were two different infrastructures. Information and energy flow were in a different directions and they were separated. But when we create the concept of smarter grids, what we are doing now is integrating the energy flow that now using a small distribute generation, also using demand response, also using electrical vehicles. Now we can control more the flexibility of the electrical system and modify the energy flow. But in order to make these multi-elements working together in a proper, secure fashion and economic, of course, we need that the information must be able to be provided to all the parties in order to take decisions. So the smarter grid is basically when this energy infrastructure is meeting with the infrastructure related to information, communication, technologies. So as you can see over here, we have this cloud over here, and this cloud is basically representing the domain of the information, communication, and technologies. If you look over here, we have technologies coming from the mobile phone, the fixed phone, the wireless, the modem, the satellite, the wide area network, internet, also concentrators, servers, and devices. So here in the middle, what we have is basically what we understand as the information communication technology infrastructure. But outside, you can see that we have in this slide, outside that cloud over there, we have generation, transmission, substation, distribution, customers, and all of these are members, actors related to what we call the classical electrical power system. And with the new paradigm of distribute energy resources, so the integration of distribute energy resources, condition monitoring, assess optimization, workforce effectiveness, start to be very, very useful. So what I am trying to tell you with this slide is that basically you can consider the smarter grid as the combination of those two infrastructures. One infrastructure that is coming from the basically the traditional electrical power system that we have been working with him for many, many decades or almost more than a century. And then we have these novel technologies that we call information, automation, control, and communication. So in other words, two different technologies are converging into a very useful and new paradigm for the energy systems. So now what I want to talk with all of you is about this natural evolution. To be honest, this is evolution. This is no disruption. This is no revolution. This is evolution. What I will show you now, if you look here in this slide, is a timeline that you can see different of the technologies involved in the modern electrical system. So you can see over here that we can say that in 1800s, Alessandro Volta, this famous Italian scientist, they invented the electric battery. And from there, 1 year later, our marvelous and very genius Michael Faraday discovered the electromagnetic induction. 1878 is the moment that we have the incandescent lamp and we start to create a proper use for the electricity. And we start to create the possible service coming from the electricity for lighting. 1882 is the moment that we start to use DC street lighting. But in 1886, we start to use the AC system, and that is the moment where the electrical power system start to increase. I will say that one massive step forward was the creation by Nikola Tesla about the induction motor. Because now we can use a device in order to create mechanical power. And with that mechanical power, well, the industry start to change and start to use many, many other features. So 1890s was the proliferation of the AC power. So years later, well, something new started to happen. The AC systems, they were working very fine, but suddenly we have a very interesting disruption because we have, on the other hand, the electronics. And the electronics suddenly start to be part, or it can be part of the AC system. So in 1957, we have the invention, and this is invention of the thyristor. So over here, you can see that 1954, 3 years before, was the first solar cell. You can see over here that in 1960, the concept of digital twin start. To be honest, the concept of digital twin is nothing new. It start in 1960 with the NASA, with the Apollo project. 1976 is the creation of a commercial product that is an evolution in power electronics, a massive step forward that is called the MOSFET. 1980s is another technology that is the invention of the IGBT, that today is the most useful device for power electronic converters, especially if you are using voltage source converter. 1980s and 90s is where the markets appear for the electrical systems. And you can see over here between 1990s and 2000 is where the interconnection of PV system and wind power start to take off. 2003, 2004 is when we start to create the concept of distribute energy resources and apply into the traditional electrical systems. So the next slide is probably the most relevant for all of us, Because in this slide over here, I can show you many of the technologies that right now, today, 2025, they are part of the concept of smart grid and also the next generation that is coming. So 1995 is a very important step forward because those measurement devices that we used to have in the past, they were not time synchronized. So the IEEE 1344, it was the concept of the synchrophasers. And synchrophaser is today one of the most used technology for operation of very large power systems. 1987 is where the concept of virtual power plants appear, and together with 1999 and 2000 is where the concept of Internet of Things it appeared, together with the amazing standard, the IEC 61850, that is more than a communication protocol and define many of the features that we will be discussing for the next 5 days. The official definition of a smart grid appeared in 2007 based on this publication created in 2005 by our colleague and friend Gus Wallenberg. So in 2007, the concept of smart grid appeared in the energy independent security. 2006 was here in Europe, but also in 2006 is when there is the first use of the concept of cyber physical systems. Helen Gill, one of the U.S. National Science Foundation, introduced the concept of the cyber physical system in one of the amazing conferences, the NSF. So 2011 is the point where we start to use Internet of Things in energy, and the concept of Internet of Energy appear. And very interesting, 2020 is when we start to push forward quite hard the concept of digital twin, also the awareness and also the interest on cybersecurity take off. So 2023 is a very important aspect. There is a colleague that later will talk about digital twins, but 2023 is where the ISO and the IC create this very important standard, that is the 30173, that is the digital twin concept and technology. 2024 is where grid edge concept appear, and the IEEE release a technical framework for digital twins, electric utilities addressing the interoperability, climate adaptation, age, and so on. And 2025 is basically when this concept of grid edge start to take off. So as you can see, the technology has evolved. Yes, the technology has evolved, starting from analog, going to digital. Then we start to combine this digital technology between hardware and software, and cyber physical systems appear. And then as the computational power increase and the communication speed start to increase, we start to use Internet of Things and then the digital twin. So this is a very interesting and very important evolution of the technologies. But let me keep talking about the smart grids. So if you look over here, there are many technologies involved with the smart grid. Communication is one that I already told you that is very, very important. But related with that is the use of the information and the data management. So communication and information, they are two very important base concept for the development of the smart grid. But when you have communication, you start to have some interest in keeping safe the data and the information, and that is where cybersecurity starts to be extremely important. And these technologies, they allow the electrical power system to behave in a very organized, optimized, and more efficient in general sense. So we start to create demand response in terms of electricity price. We can start to use this renewable energy that they have the variability and the intermittency. We can include many resources in the network, and the concept of distribution generation start to take off. We can now control those microgrids, and energy storage came as a tool for solving the variability and also the intermittency of the system. Distribution automation was a natural evolution together with the smart meters, where we start to collect the data downstairs from the bottom to the top. SCADA system data acquisition start to increase, and from there we start to create standard policies and so on. And what we are looking with those smart grids is basically enable several features that we want for many decades in the traditional electrical power system, but we didn't have the technologies to deliver. We tried to have electrical power system that was able to adapt and survive any dangerous situation. So we want self-healing. But the problem is that many decades ago, we didn't have the sensors to produce the data, we didn't have the computational power to process them, and then the control actions going back to the system. So now with the concept of a smart grid, we can enable safe healing. We can be more interactive with the market and the customers because we can install sensors directly to the customer. We can be reading data and receiving information from the market's prices and so on, all of them allowing the optimization of the resources. And today, the use of artificial intelligence and all those methods, they allow us to be more predictive in order to ensure minimizing the operation, minimizing the cost of operation, but at the same time maximizing profit benefits and, of course, security of the system. So we start to have distributed assets with information, integrating other sources of information like weather, but also the market with the price. And we start to include features like security, confidentiality, reliability, and so on. So in general sense, those are some of the features related to the smart grid. And later we will discuss a bit more, okay? So a key element of the smart grid, is the use of applications in terms of the utility operation. So many people must understand that applications, when we are talking application in the context of the utilities, power utilities or energy utilities, we are typically referring to software-based functions or tools that perform very specific tasks like control, monitoring, analyzing, automation, and so on. So there are many applications when we are talking about electrical power system. But in the context of smart grid, before the smart grid, we have basically three applications that we used to have in every single electrical system. What we call the supervisory control and data acquisition, that all of you know as SCADA system. The applications that require information coming from the field, processing and delivering some information to the data control centers, and of course, teleprotection. So those are some of the very old and primitive applications that we can have inside the utility. More detail, and probably a modern view of them, we can divide the applications into very different contexts. Some applications related to the transmission system, some applications related to the distribution management system. So in both cases, they can be centralized or they can be distributed. When we are talking about applications, you can see over here, the winner over here is the SCADA system, but in transmission and also distribution, we can have energy management system. In transmission, we have the wide area, so we can have wide area situational awareness and control, but also we have digital fault recorders. We can have some applications related to the control and operation of the flexible AC transmission system. And another traditional application in transmission system is what we call the dynamic line rating. Similarly, we can talk about different kind of applications for distribution management system, SCADA again, digital fault recordings, but specifically to distribution system, we can have the outage management system, we can have voltage, VAR, watts control, we can have the meter data management system, multi-feeder reconfigurations, and so on. So now what I will show you is a couple of examples. You can see here the traditional, the very old concept of a SCADA system. In a SCADA system, we can identify here at the very bottom here, you can see that we have the power components. We have here current transformer, voltage transformer, circuit breakers, switches, and so on. All those devices, they are primary devices connected to the high voltage system. We have here secondary coming for measurements or for automation, and even for measurements. We have a secondary circuit for tripping the circuit breaker, and all those devices, they are connected in the very at the very early stages of the technology. We use copper wires, and we are still using in some substations copper wires in order to transmit the commands or transmit the signals coming from those current transformers or voltage transformer. Then we have here the base controller, we have the protection relays that they are hardwired, they are connected directly using copper wires to the secondary equipments over here, okay? Then we can have some communication using point-to-point serial communication. So basically the SCADA system, as you must be aware, the classical SCADA system is using what we call the serial communication. In this serial communication, in a very specific channel, let's say a copper wire, what we are sending is small pieces of information that they are sent one after the other. So that is the reason that we call this series communication protocol. And there are many communication protocols that we have been using in this connection between the different base controllers and relays and the high-level functionality devices like the remote terminal units, the human-machine interfaces, the engineering computers. So typically we can use, for instance, Modbus or DMP3, as I say over here, Modbus or DNP3 as typical communication protocols for this specific application SCADA. And they are typically transmitted using a very specific and standardized configuration of copper wire, for instance, using RS234 or using RS485 copper links. So this is the traditional way, the very old way of having a SCADA system. So in the SCADA system, as I say before, we are using the traditional serial communication, and inside the serial communication, you can imagine here the structure. We have here at the top the data users. Some data is coming for a very specific channel serial communication, and this is a multiple serial communication. But also we have small devices connecting to the local RTU, remote terminal, and then sending the information using the serial communication to the data users. And this is the classical serial communication. Serial communication, as I say before, is the process where we are sending data one bit at the time, sequentially over the time communication channel or the bus. So this is, if you think about it, was useful at that moment, but this traditional mechanism start to be a bit, I will say, probably not so useful, because this point-to-point or multi-point or multi-drop configuration, of course, enable the basic telemetry and control, providing the operators the real-time data on equipment status, breaker positions, and voltage level. However, this system is quite reliable and simple. However, because there are several limitations related with the capability of this system. So there are limitations about the bandwidth that we can use in this copper-based communication channel. Also, the scalability and the interoperability. Some signal degradation over long distances. Those SCADA systems using analog signals, they are limited on the size of the substation that you can use without using amplifiers. And also there are several cybersecurity, lack of cybersecurity built-in possibilities. So that was the moment that the technology evolved and we start to use those networking information systems. In the networking communication system, as you can see over here, basically you can see that we have the communication network, and this communication network is probably something that is more familiar to the younger people. In this case, we are using packet switch information moving inside the communication network. We can have serial point-to-point, or we can have multi-drops. In this case, we can use multiple copper wires, or we can use also fiber optic or wireless communication. So in this sense, we are making a network, a communication network that is overcoming some of the challenges. Is basically scalable. You can increase the size of the communication network. The bandwidth is even higher, and that's moved the SCADA system to the net phase, making the refreshment faster and getting information in a faster fashion. But now, how this network architecture, how those communication protocols, they are related to the to basically the electrical power system and the smart grid. So if we go to think about the configuration and the architecture of a smart grid, considering the North America vision, you can see that over here, the National Institute of Standard Technology, or also called NIST, they have a very well-defined architecture. So this architecture is basically that the way that we define properties of the system, the environment, and the elements, relationship, principles, and design. So in this document that you can see over here, I believe you can see that I include the link over here below. You can go to that link and you can download this very exciting document. This is a document from July 2020 that you can see the Smart Grid Interoperability Standard. This is the release number 4. So basically the concept coming from the United States, they include several domains. You can see that they are the generation, the transmission, the distribution, and the customers. Those domains are related to the critical and basic activities inside the utilities, but also we have here operation, that is what is controlling and doing so many other things. We have the economic part related to the markets, and we have services provider to close the full loop. So in the American vision, you can see that we can have the generation domain, and inside the generation domain we have large generators, centralized generation, but also we can have several different technologies: biomass, geothermal, pumped storage, nuclear, coal, gas, wind, solar, and all of them they are feeding this kind of energy into the transmission domain or the distribution domain. Also, the customer can be injected or receiving this kind of energy from those different technologies. So there are different physical actors. There are physical actors like the protection relay, the remote terminal units, and many other things like the file recorders and so on. And of course, many applications, software-based, are defined in this very specific domain where we want to control, measure, protect, record, and assess management. Transmission, of course, is a very exciting domain. Inside the transmission system, what we are doing is moving those very large blocks of energy, and we have different physical actors like the substation meters, protection relays, but all of them located at the transmission level. And there are many applications, including, for instance, substation applications for control, security, measurements, and so on, but also for the control. Then we have here the customer domain. In the customer domain, of course, we have different elements, like we have the meter that we have at home, but we can have several appliances, the thermostat, the local generation, the automation, and so on. We can combine that with the industry. We can have also commercial participants or actors. So this is a very complex domain, but also this domain is interacting with service providers, operations, and the other domains. One very exciting domain is the one related with markets, because the markets, and they can allow the interaction now of the customer and the data provided by the customer. So in that way, we have different domain interfaces working together, allowing communication flow between markets domain and the other domains, like the supply of energy and the critical use of that. So there are many applications over here, especially related to market management, to aggregators of the very different distributed energy resources, but also service providers, secondary service providers, and so on. Here now we have the provider domain. In the provider domain, basically what we have is the interaction between customer management, account management, emerging services, billing, installation, building management, home management, all those services that they support the electricity business. And finally, here we have in front of you, you have here what we call the operation domain. And the operation domain, as you can see over here, what we are doing is the whole operation of the system. So we have interaction, we have interfaces with the other domains, including transmission, distribution, customer, but also service providers, markets, and so on. So that is the vision that was created by the NIST, the Conceptual Model of a Smart Grid Architecture in the United States. But what is happening in Europe is a bit different. The fundamental concept related to the system and all the components, they are defining the architecture. And in Europe, three standardizing organizations: the European Committee for Standardization, CEN, the European Committee for Electromechanical Standardization, CENELEC, ETSI, that is the European Telecommunication Standards. They work together in this smart grid coordination group. And in general sense, they create the smart grid architecture in Europe, that you can see over here, that we have the smart energy grid architecture module that is called SGAM. And basically there are three axes, one of them related to the business, one related to the architecture, and one related to the interoperability. If you look over here, the basic foundation of the architecture model is simpler. We have one for business, that is basically the domains. We have the architecture, that is basically the zones. And we have the interoperability that is connected to the levels. So you can see over here, this is basically the smart grid plane that we are indicating in this plane, what we call the domains and the hierarchical zones. If you look here in this axis, we have the classical domains: generation, transmission, distribution, distribute energy resources, and customers. So in this way, in what we call here the domains, basically what we are describing is the complete electrical energy conversion chain. And here on this side, we have the zones. And the zones are basically places for data aggregation, spatial aggregation. And you can see that the low level over here is connected to the process, and the high level over there is related to the market. In the middle, we have the field, the station, the operation, and the enterprise. So we have information management that is connecting those different domains and those different zones. And now what I will show you is the different framework. We already covered over here the component layer, that we have the domains and the zones. But then we have the communication layer, that is basically where we describe the protocol and the mechanism for exchanging information between the different components. Then we have the information layer that is related with the data model, basically describe the information that we are using and exchanging between different functions. And the next layer, layer number 4, is the function layer, that basically we are describing functions, services, and the relationship, but in this case from the architecture point of view. And the last and probably the highest of those layers is the business layer. And in this case, we have basically where we are representing the information exchange related to the smart grid. So as you can see, the concept of a smart grid is involved two different visions, but both of them, they have similar elements related to what we call in this case, what we call the basic hardware and the software. So as I was explaining about the natural evolution, the cyber-physical system, it was a natural evolution. To be honest, at the very beginning of the power utilities, we were using basically physical layers, because we were using electromechanical devices that we have hardwired to the electrical system. So everything was at the physical layer. But with the integration of digital technologies or analog technologies, including networking, well, we start to create this cyber-physical system. And if we go for a standardized definition of cyber-physical system, ISO emphasized that the cyber-physical system is where the information processing and the physical processing interact, and in this case using networks. And to be honest, this is the key for smart grid, smart cities, autonomous vehicles, industrial automation, and so on. There is a history that say that cyber physical systems are coming from the automotive industry. Don't believe me, but what you need to understand is that basically we have all those physical devices here inside the electrical or energy system, and they are just the physical devices. And on the top of that, you can imagine another layer, and in this layer we have what we call the cyber layer, that we have information processes, and that involve networking and computation. When we combine all of those things together, well, of course, we have the cyber physical system. And I need to tell you about cyber physical systems because if you remember, we were talking about the SCADA system. And to be honest, the original SCADA system was a cyber physical system because we used to have here the physical layer with the physical devices, the transformer, the buses, the capacitors, the circuit breakers, and so on. And there is a flow of data and information that can be real-time measurements and command controls. And on the top, we have here the SCADA, where that data is processed in order to take decisions. So cyber physical system has been for many years in electrical systems, but most recently have taken a lot of interest because the use of very specialized industrial communication protocols, they have created so many good features that we can take now and we can use. For instance, the concept of digital substations. So digital substations are taking the advantages of this digitalization and this virtualized process in order to make more efficient, reliable, and resilient the functionalities of automation, control, and protection. So nowadays, everything is smart and digital. And right now, I will show you some of the smart grid applications. And there are many smart grid applications. For instance, advanced metering infrastructure. For instance, distributed automation, some controllers related to distributed generation and distributed storage. Today, we can create a cluster, a swarm of electric vehicles, and we can offer services to the grid. We can integrate many microgrids into a microgrids in order to offer services. The home area network that is related to communication protocols and making the things talk together by using Internet of Things is opening the door for deliver new services. Wide area situational control and so on is a reality. Control of flexible AC systems and dynamic line rating. As you can see, the list is a very limited list. There are more applications that we can talk about, and I will not have the time to present all of you today. However, one of the very interesting applications is advanced metering. Many countries are developing and using smart meters, and those smart meters, they can communicate directly to what we call the data and control center. Many of the smart grid now, they are following a communication protocol, the ANSI C12.19, but also there are the possibility that all these smart meters, they can communicate together inside what we call the neighborhood area network. There is a meter concentrator, and then they send the data over the data and control center. This later approach is the one that is vendor proprietary. This is advanced metering infrastructure based on vendor proprietary, because this is allowing also some encryption and data protection, okay? Another interesting step is distribution automation. Now we have very fast and reliable communication channels, and we have sensors deployed in many areas that we never imagined before inside the distribution system, and also different environments. We can have now physical signal for the temperature of the transformer, vibration, infrared, and so on. So data automation refers to using all the functions related to distribution system, but taking advantage of the information. So basically, we moved all that data and the information and the actions using here the communication network, and then we can have decentralized or distributed data centers. Okay. So it's time to show you some of the applications. For instance, one smart grid application that I like and is related with distribute automation is basically this one. All of you are related with the power utilities, and one of the most challenging situations is the detection of the high impedance fault. High impedance faults, as the name say, is a high impedance that is connected to one line or two lines to the ground, and is characterized because the current that is moving during the fault condition is relatively small and probably comparable with the low current. So one way that we publish a paper where we are using digital technologies is basically enabling the use of a digital communication protocol, industrial digital communication protocol like the IC61850. So you can have a distribution system, and in this distribution system, of course, if we are using the classical overhead distribution system, we can have this kind of reconnectors. So in this case, what we are doing with these reclosers are basically, we use these auto recloser laws of phase protection, and we use the IC61850.8.1. In other words, we use the Goose protocol to detect and isolate the broken conductor. In this case, when the fault occurs, you can see that one of the reclosers is indicating that the voltage in one of the line is 0, and the other one is indicating the same. So there is a current interruption and also a voltage difference between the terminals. So the reclosers take the signal, generate a goose, and they communicate using a goose protocol. So this is one of the publication. It was 2023. Over here, I want to show you another publication. Sorry, I forgot to mention the credits. This publication was with the colleague from Schneider Electric and also from the Universidade Tecnológica Federal do Paraná in Brazil. Okay. So another application here of cyber physical systems and digital substation, it was related to optimizing the operation. And in this case, we are talking about DC-AC microgrids. We have a cluster of AC-DC microgrids. And in this case, what we are using is a digital communication protocol, a socket protocol, in order to work over the PLL. And in this case, we are enable the converter, the power electronic converter, the DC-AC converter, working as grid forming or islanding or in a grid feeding connection. And in this case, what we are using is basically a real-time simulator. You can see here, this is the very famous Nova Core. And in this case, we are streaming data of voltage, frequency, the power, load, and the state of charge. And we have here the Ethernet, where we have the whole communication network. And In this sense, we are taking the decisions based in this algorithm, and using communication signals, we can change or modify the operation control mode of the converter. In this case, this is a collaboration with the Indian Institute of Technology. You can recognize here, this is the Indian Institute of Technology in Jammu with my very good friend Anup Chulka. Another example over here is the distribute automation using optimized operation. And as you can see over here, we are using communication protocols, we are using co-simulation. Now we are using the real-time simulator coming from Typhoon Hill. And in this case, we have the IEEE 39 bus bar system. You can see here voltages and current running in real-time simulation. And if there is any change on the loads or any change on those renewable generation, automatically we will generate using phasor measurement units C37118. We will generate data streams that they are sent to the cyber layer, and in this cyber layer, of course, we are running a algorithm, and in this case, the algorithm is basically a optimization algorithm that what is doing is, if there is a mismatch between generation and demand, is redispatching the generation and sending back signals to the physical layer to reconduct the redispatch. And in this case, we are using the protocol, the industrial protocol IC61850 as mechanism to close the loop. And in this case, we can reach an optimized operation. On the top over here, you can see the QR code. You can read that by scanning that code. Another concept related to very important evolution of the smart grid is what we call the digital twin. A colleague will talk with more details about digital twin. What you need to understand is that the digital twin has been already standardized. If you follow the ICO IC 30173, that is basically the digital twin concept and terminology. And in that standard is defined a digital twin as a digital representation of a target entity with data connections that enable convergence between the physical and the digital states in an appropriate rate of synchronization. In other words, we have the target entity, and this can be an electrical power system or a single device like a transformer. There is a data connection, and that means that we have real or near to real-time links in order to allow digital twin to reflect changes on the physical counterpart. We have convergence, and that convergence means that we have an alignment between the digital and the physical state of the target entity, and we have a synchronizing rate that is basically the frequency that we are updating those states, and in this case can be from milliseconds up to more. So if you allow me, I will show you an example of a digital twin, and I will start with something very simple. You must know that one interesting feature that we have is the protection relays. The protection relays, they are basically hardware that they are installed in the system. So when we want to test the functionality and the characteristic of those protection relays, we can use several approaches. One of them is use a digital real-time simulator that here we can have, for instance, an electric network. And here we are sending low power signals to this power amplifier. We are injecting high current and high voltages to the real device, and then we are sending feedback of the operation and the condition of this real physical device. So this is what we call hardware in the loop. I prefer to use the name relay in the loop. In the relay in the loop, you can see over here, I have the real-time simulator. This is the Hill 604 coming from Typhoon Hill. We have a real protection device. This is the hardware, the cell SEL751. And we have here the universal Hill Connect, that is the power amplifier. To show you all the mess related to the cables, you can see this is the hard wiring. You can see the wires coming from the power amplifier, and here at the back we have the real hard wiring. However, with the evolution of the digital communication, the IC61850, they allow now that these relays, these ID intelligent electronic devices, instead of using analog signal of voltages and currents, they can use 1 and 0 or digital data in order to process and act as automation, control, or protection device. So the concept of the merging unit or receiving directly a digital signal from non-conventional voltage transformers and current transformers that allow the creation of those digital substations. So I use the Opal RT, I use the Opal RT framework, and basically what we have here is this is the representation. This is the representation of, in this case, electric network. And in this electric network, as you can see over here, we are creating that inside Simulink and then imported into RT Lab. When the model is compiled, it's going into the real-time simulator. In this case, the target is a Opal RT OP4510. And when it's running in real time, is reproducing this system, creating those voltages and current. And then we are using the communication protocol, digital communication protocol, in this case, the IC61850. And we are creating digital samples of voltages and current using the sample values. The sample values are going into an industrial switch. And we can use any software, sniffer software like Wireshark, in order to monitor the data and the package flow inside the network. And these sample values are going inside to the digital relay. The sample values are just basically digital data that represent the three-phase voltages and current. And with that, the relay is able to perform the activities, automation, control, protections. And assuming that there is a fault condition, this relay will generate a trip signal. This trip signal, we use the very important goose, signal. In this case, this is one of the element services coming from the IC61850. And this goose signal is going back to the digital real-time simulator. And when this goose arrives to the digital real-time simulator, is basically representing the signal that is ordering the open of this circuit breaker in order to stop the fault. So here what we are doing is basically using a concept of cyber physical system. We have the physical layer with all the hardware, switch, real-time simulators, but also we have the cybernetic layer where we have this digital replica of the electrical system, but also we have here all those communication protocols that they allow us to do the job. Another example is in this publication, and in this case we use the concept of digital twin. We use one of the Typhoon Hill 604 in order to create a digital replica of the electrical power system. We call this the virtualized physical layer, and we are sending sample values and receiving goose. And on the other real-time simulator, we have the virtualized protection. In other words, we have an overcurrent protection relay that is simulated inside the cyber physical layer. So as you can see, virtually we can do anything to replicate any physical condition, real physical condition, using digital real-time simulators and using the concept of cyber physical system. Well, I am really sad because we are almost finishing this, but it's the moment of a small summary. The first thing that I want to tell you is that a smart grid is a very interesting concept, but is a natural evolution, is an evolution of the technology. And we are expecting that more and more technologies are appearing, and it will create more and more changes in the way that we are producing electricity, delivering electricity, and consuming electricity. However, it's my personal feeling that I show you here a lot of technological evolution, but we need to cope with many, many challenges and very difficult challenges. That is my impression, that we need a disruptive technology. I highly suggest that you reflect about disruptive technologies in order to move forward and to create the next generation of digital energy system. So before I go, I would like to express my gratitude. Many people have been inside the lab. All of them has a lot of contributions into the lab, practical contribution, ideas, collaborations, and so on. From my colleague, you can see over here, we are talking today in India, and this is my very good friend, Dr. Anuj Shulka from IIT Jammu, when he stays 6 months with us in the research lab. He's a very good friend of mine. We are still collaborating, and he has an amazing real-time simulation hardware in the loop laboratory over there in India. I congratulate him and his team and all the PhD students over there. Finally, I would like to express the gratitude. This gratitude is to all the collaborators, partners, sponsors, or whatever the name you want to use, ABB, Arbiter System, friends of Opal RT, that we have very close collaboration together with Typhoon Hill, my friends over there, Nicole and Ivan, Omicron, IPSA, also Schweitzer, that has been supporting the lab for many years, and my closest friend, I will say that I have a collaboration that probably is longer than 25 years with Power Factory. So before we close, I would like to say, please stay in touch. Some of the colleagues are attending to the PAC World, Protection Automation Control Worldwide. It will be a conference in North Carolina in the US. If you have time, approach over there, because we will show one of the first demonstration of routable goods, and it was an implementation in Peru with the collaboration with Siemens and Omicron and the people from ISA. Also, we are showing some of the new developments on the power electronic converters, especially with negative sequence injection and testing. So this is a very nice collaboration with the people from Omicron Electronics. Finally, I will be in the IEEE ISGT, Smart Grid Technologies, Innovative Smart Grid Technologies in Latin America. Over there, I will be delivering on 16th of September a couple of tutorials understanding the IC61950, process bus and digital substation, and also tendencies of modeling and simulation using Power Factory. And if you have the time and you are attending to the IEEE Power and Energy Society Generation, Transmission and Distribution Conference and Exposition 2025 in Thailand, I will have the pleasure to be delivering this tutorial. Is the IC61950 process bus and digital substation concepts and real-time simulation. And this is a very, very nice collaboration. It will be an impressive tutorial with my colleagues and friend of PTS Combination, a very nice Thai company, and also the collaborator from Opal RT Technologies. So we are reaching the end of this video. Again, I'm really sad that I'm not there with all of you, especially I'm not in real time over there with all of you during this very first section. But it was my pleasure to introduce the concept of smart grids and also talk about the architecture and features and showing you some of the concept. So if you have the possibility and you have any question, please drop an email, communicate, and we are open for collaboration. So this is all for my presentation today, and it's time to say bye now.